Good morning. Today we will be going over the sliding filament theory, which describes the mechanism that allows the muscles to contract at a cellular level. So what is involved in this process? Well, it occurs in the skeletal muscles in the muscle fiber. These bundles of muscle fibers can contain anywhere from 10 to 100 individual fibers. Inside each muscle fiber is a myofibrils, which are bundles of specialized proteins called actin, which are thin filaments, and myosin, which are thick filaments. The myofibril is surrounded by what is called the sarcoplasmic reticulum, which is a network of tubules and channels. Calcium is stored and released here, and each myofibril can be broken down into functional repeating segments called sarcomeres. T-tubules are tubes formed by protrusion of the sarcolemma deep into the cell interior. Their function allows for electrical nerve transmissions to reach deep into the interior of each muscle fiber. How do they all function together? So a sarcomere ends on its Z-line, and these Z-lines are where the thin actin attaches. The thick filaments are held attached by the M-line. The sarcomere must shorten for muscles to contract, but the filaments themselves do not shorten. When the sarcomere contracts, the thin actin is pulled by the thick myosin towards the center. This causes an overlap of thick and thin filaments, and the Z-line moves closer together. Taking a closer look on how this works, actin is displayed at the top while myosin is displayed at the bottom with a myosin head. These hundreds of myosin heads are bound to ATP. When the myosin head hydrolyzes the ATP, it results in ADP and a phosphate. This leaves an opening for the myosin head to attach to the actin, creating a cross bridge, allowing the myosin to release the ADP and the phosphate and perform a power stroke, meaning the thin filament slides towards the sarcomere center. A new ATP attaches to the myosin head when it is detached from the thin filament. Without this new ATP, rigor mortis will occur. Hundreds of cross bridges happen throughout a muscle contraction because there is so many attached throughout a contraction and throughout the muscle fibers. It prevents the actin from slipping back into its original position. Muscles aren't always contracting, and there is a regulation that takes charge of this process. Actin is able to regulate myosin heads due to it having tropomyosin on it, a regulatory protein that blocks myosin binding sites on actin. Troponin is also a regulatory protein on the thin filament line. When a neuron stimulates a muscle, it can trigger a release of calcium, and the calcium ions bind to the troponin. This change lets the tropomyosin move off the myosin binding sites, allowing the myosin head to attach to the actin. When looking at how these muscles contract in response to stimuli, the contraction produces muscle tension and the force exerted on the load or object to be moved. These contractions are either isometric or isotonic, no shortening due to not exceeding the load, or muscle shortens because tension exceeds the load. Isometric contraction could be comparable to picking up an immovable or heavy object, while isotonic contractions could be comparable to picking up an obtainable weight. There is also a change in results even though the electrochemical and mechanical events are the same. Isotonic contractions have actin filament shorten and cause movement, while isometric contractions cross bridges generate force, but the actin filaments do not shorten, causing the myosin heads to spin on the same actin binding site. The energy required for muscle contraction takes a toll on energy preserves. Because of this, neurons recruit on a principle based on size. Smallest muscle fibers are recruited first, and as stimulus intensifies, so does larger fibers. This energy used during the process is recollected in three different ways. ATP to PCR is a direct phosphorylation of ADP by phosphocreatine. PCR is a unique molecule located in muscle fibers that donates a phosphate to ADP to instantly form ATP. Muscle fibers have enough ATP and PCR reserves to power cells for about 3 to 15 seconds. The second way is the glycolytic anaerobic pathway, where ATP is generated by breaking down and using energy stored in glucose. This does not require oxygen, and glucose is broken down into 2 pyruvic acid molecules. Low oxygen levels prevent the acid from entering aerobic respiration phase. This yields only 5% as much ATP as aerobic respiration, but produces the ATP 2.5 times faster. The aerobic respiration is the final mechanism for ATP regeneration. It produces 95% of ATP during rest and light to moderate exercise. This consists of a series of chemical reactions that occurs in the mitochondria and require oxygen. This process breaks down glucose into CO2, H2O, and large amounts of ATP. It can restore 32 ATP per glucose, 36 per glycogen, and over 100 per fat. This concludes my presentation for the sliding filament theory. If you have any questions, please feel free to ask them. Other than that, you have a great day.